Welcome to Lecture 12 of Physics 506. In this lecture, we're going to do our first of two lectures on the addition of angular momentum. We're going to start by assuming that we have two angular momenta which are completely independent and commute with each other. So you could think of this as the orbital angular momentum of an electron in an atom and the spin angular momentum of the electron. Those are two completely different objects and they commute with each other. The key is that the two angular momenta that we're working with, that we're going to call J1 hat and J2 hat, that they commute with each other. Now they are angular momentum, so they satisfy the normal commutation relations of a vector operator when you look at the commutation relations of the J1 components with itself and of the J2 components with itself, but the commutator between any J1 component and J2 component is equal to 0. Then we construct what we call the total angular momentum operator, which is J1 plus J2. And now we're going to compute the algebra of J1 plus J2. So we're going to look at the commutator of J1 plus J2. We simply substitute in the definition. So I get a J1I plus J2I commutator with a J1J plus J2J. Now there are four terms here, but the cross terms are all 0 because the commutator of J1 with the J2 is always equal to 0. And when we look at the commutators of the J1I with the J1J and the J2I with the J2J, they're both the same form. I get an IH bar epsilon IJK J1K, and I get an IH bar epsilon IJK J2K. So I can add those together. And indeed, we find that the total angular momentum satisfies the same commutation rule as angular momentum satisfies. Now, using that fact, we are now going to claim that J1 squared, J2 squared, J1Z, and J2Z all commute. So we're going to go through this carefully to verify that they all commute. Now, the claim is that this is obvious. The one terms all commute with the two terms. So J1 squared commutes with J2 squared and J2Z, and J2 squared commutes with J1 squared and J1Z. So if I look at the J1 squared operator, the only thing remaining that I have to verify it commutes with is J1Z. But we know J1 squared commutes with J1Z. That's one of the properties of angular momentum. And if I look at the J2 squared operator, the only thing that doesn't obviously commute with is the J2Z. But again, we know J2 squared commutes with J2Z. And so this means that all possible pairs of operators in that set of four operators, they all commute. That means that they're a maximally commuting set, and I can construct eigenfunctions that have eigenvalues with respect to all four of those operators. Now we're going to call those eigenvalues J1, M1, J2, M2 with the obvious definitions for each of them. The J1 is the quantum number corresponding to the J1 squared operator. The J2 is the quantum number corresponding to the J2 squared operator. M1 is the quantum number corresponding to the J1Z, and M2 is the commutator corresponding to the J2Z. Okay? Now, but that's not it. There's another set of four operators that mutually commute. We can look at the total J squared, the total JZ, J1 squared, and J2 squared. Those also all commute. So let's first look at the commutator of JZ with J1 squared. Well, JZ is just equal to J1Z plus J2Z. J2Z commutes with J1 squared, but so does J1Z commute with J1 squared, so that commutator is 0. Similarly, JZ with J2 squared is equal to 0. Now we have to verify J squared commutated with JZ is equal to 0 because the J is an angular momentum operator. It satisfies the angular momentum algebra, which means that J squared and JZ commute, just like it does with any angular momentum operator. Okay, now we have to then carefully look at the commutation relations between J squared and J1 squared and J squared and J2 squared. So the claim is the commutator of J squared with J1 squared is equal to 0. We get that by writing out what J squared is. So it's equal to J1 squared plus 2 J1 dot J2. So that's going to be J1x J2x plus J1y J2y plus J1z J2z plus j2 squared. So we're going to now carefully go through and verify that the commutator of j squared with j1 squared is equal to 0. So after writing out that j squared is equal to j1 squared plus 2j1j, j2j plus j2j squared, we've already verified that the j1 squared and the j2 squared from the j squared, they both commute with j1 squared, so they're gone. j2j also commutes with j1 squared. So when I use the Leibniz rule on that cross term, I just have to verify that j1 squared commutes with j1j. But of course that's true because that's true for every angular momentum. So that then means that j squared commutes with j1 squared. And then similarly, using a very similar argument, you can verify that j squared commutes with j2 squared. Okay, so then these four operators are also a maximally commuting set of operators. Total angular momentum squared, z component of total angular momentum of 1 squared, and total angular momentum of 2 squared. So we now have another set of eigenstates that we're going to label by total angular momentum quantum number j, total z component of angular momentum quantum number mj, total angular momentum of 1 j1, and total angular momentum of 2 j2. And the operators, when they act on the states, are given by this set of 4 equations here. I'm not going to read them out for you, but they're pretty obvious given what those quantum numbers are, exactly what those eigenvalue-eigenvector relationships are. Now, both of these representations are equivalent to each other, and they span the whole basis of states for angular momentum. And that gives rise now to a couple of questions. Given a j1 and a j2, what values of j are allowed? And second, how do I convert between the different bases? So because these are two equivalent bases that I can write any state that corresponds to the total angular momentum between these two objects in terms of these different basis states, there should be a conversion from one basis to the other basis. And the coefficients of those conversions are called Clebsch-Gordan coefficients. And that's in essence what we're going to be focusing on for the rest of the lecture, is talking about these different properties. And in the second part of the lecture, we'll ultimately end up with a procedure by which we can calculate these Clebsch-Gordan coefficients. Or if you like the expansion, understand how we represent the different angular momentum wave functions in these two different bases. All right, so let's assume we start with two states. The first one has a total angular momentum given by a quantum number j1, the second one with a quantum number j2. Those values are fixed, and we want to look at the states that are represented by the angular momentum quantum number for system 1 called j1, the z component m1, the same for system 2 with a j2 and an m2. Now, so it's easy to figure out what the total z component is because that operator actually also commutes with the j1 squared, j1z, j2 squared, j2z. You can easily verify that j total z commutes with those guys. So it's already an eigenstate of those. And you get that because you can write the jz as j1z plus j2z, and that state is an eigenstate of j1z and of j2z. So you get h bar m1 plus m2 quantity times the state j1, m1, j2, m2. So that's one thing that is nice. The jz operator, it's already an eigenstate. I don't have to do anything with it. But in general, this state is not an eigenstate of total j squared. So let's take a look at the maximal spin state. So the maximal spin state has an eigenvalue when given by m1 equals j1 and m2 is equal to j2, which means the total m, the quantum number for j total z, is j1 plus j2. I just add up m1 plus m2, it's equal to j1 plus j2. This is the maximal mg that we can have, so that must be the maximal value of the total angular momentum j, because the z component of angular momentum is never bigger than the quantum number that corresponds to the square of the angular momentum. So if I have a state that has an m that's equal to j1 plus j2, I must have a j that is at least as big as j1 plus j2. But because I don't have any states that have angular momentum j1 plus z component of angular momentum that's j1 plus j2 plus 1, I can't have a j value that's bigger than j1 plus j2. So that is the maximal j value that I can have. In other words, the state j equals j1 plus j2, mj equals j1 plus j2, j1 comma j2 is going to equal the state j1, m1 equals j1, j2, m2 equals j2 up to a global phase. Now I'm going to just slow down for a moment here because I really want to make sure you understand this. I find when people are working with angular momentum and adding together and combining angular momentum, this fact they forget very, very quickly. And this fact is the key that you need to do anything in terms of working with total angular momentum states. So I really want to make sure that you understand this logic that we use. So I'm going to very quickly say it again. This has the maximal value of the z component of total angular momentum, which is j1 plus j2. That must equal the maximal j because the z component of spin is never bigger than the angular momentum corresponding to the squared angular momentum operator. And that means that these two states, since there's only one of them, these two states must be the same up to a global phase. All right, now, similarly, if I look at the smallest, the most negative value of jz, so j1, m1 equals minus j1, j2, m2 equals minus j2, that is the state j equals j1 plus j2, mj equals minus j1 minus j2, j1 comma j2 up to a global phase by exactly the same reasoning and logic. Okay, so we've found at least two states that we can figure out exactly what they are. How do we find the state that has j1 plus j2 minus 1? Well, let's start to look with the maximal mj states that I can have that. So those would be states that have an mj equal to j1 plus j2 minus 1. Well, there are two ways I can find a state with that value of mj. I can have j1, m1 equals j1 minus 1, j2, mj equals j2. I also can have j1, m1 equals j1, j2, m2 equals j2 minus 1. And so this state is a linear combination of these two states. That means that there's a second state in here, and the second state is the state that has total mj equal to j1 plus j2 minus 1, and a total j equal to j1 plus j2, because I have to have that state as well. So the question is now, how do we find them? Now, the only thing that we can use is the raising and lowering operator. That's the only thing that can convert from one state to another. So if I take that maximal mj state, jmj equals j1, j2, and I hit it with a j minus operator, that is proportional to the state jmj equals j minus 1, j1, j2. So what we do is we take that maximal state, which was unique and we knew, we hit it with a j minus. That state is the state that has j equals j1 plus j2. And then we simply find the state that's orthogonal to that. There are only two states, so one of the states is orthogonal to that in the space. That's the state that has j equals j1 plus j2 minus 1. Now again, I'm going to pause for just a second to make sure that you're clear on how this works, because again, this is critical to being able to work with these states. When I look at this state that has mj one less than the maximal allowed value of mj, I have a representative that has total j equals j1 plus j2 and a representative that has total j equals j1 plus j2 minus 1 in terms of the linear combination of those two states. And since there are only two states, the dimensionality of the space is 2. So there's one linear combination that has j1 plus j2 and one linear combination that has j1 plus j2 minus 1. So if I can find one of the linear combinations, the other one is simply the orthogonal state to that, because that then spans the space. All right? So that's a really important concept, again, for you to understand and follow. All right. Now, if we go one less, we just keep up the same procedure. So now we have three states. We have a state that has m1 equals j1, m2 equals j2 minus 2. We have m1 equals j1 minus 1, m2 equals j2 minus 1. We have m1 equals j1 minus 2, m2 equals j2. And that's it. There's only three states that have mj equals j1 plus j2 minus 2. Now, again, we know that the three possible values of j are j1 plus j2, j1 plus j2 minus 1, and j equals j1 plus j2 minus 2. There are three states in there. We get the state with j equals j1 plus j2 by hitting our previous state that had j and mj equals j1 plus j2 minus 1 with another j minus. We get the state that has j equals j1 plus j2 minus 1 by hitting that state that we found before, the maximal mj state with j1 plus j2 minus 1. And we hit that with a j minus. And then the state that is perpendicular to those two states is the state that has j equals j1 plus j2 minus 2. And you can see that you can just repeat this, okay? Now, you obviously also can see it gets very tedious and hard to figure out what this is if you're going to be trying to do it on your own without any other further guidance. But in principle, you could do it if you really had to. All right. Now, let's try and count the total number of states. Let's suppose j1 is bigger than or equal to j2. That means the largest m is j1 plus j2. That's, of course, always true. And the largest j is j1 plus j2. But the smallest j is not necessarily 0 or a half. It's actually equal to the absolute value of j1 minus j2, which is what we call j minimum. And let's see why this is true by working on an example where I have a j1 equals 2 and a j2 equals 1. So we're going to work now. I'm going to just look at all possible states that have the different values of mj. So the largest value of mj is 3. That requires m1 to be 2, m2 to be 1. The states that have mj equals 2, I could have 2, 0, or 1, 1. The states with m equals 1, I can have 2 minus 1, 1, 0, or 0, 1. The states with m equals 0, I can have 1 minus 1, 0, 0, or minus 1, 1. I'm going to move this up just a little bit here. The states with m equals minus 1, I can have 0, minus 1, minus 1, 0, minus 2, 1. With minus 2, I have minus 1, minus 1, minus 2, 0, and with minus 3, I have minus 2, minus 1. There are no other combinations that I can have. So now let's just work with using the dimensionality of the space and figure out what j values we're allowed. When mj is equal to 3, that's obviously j equals 3 from the arguments we're using before. When m equals 2, we know that we have j equals 3 and j equals 2. When m equals 1, we have j equals 3, 2, and 1. But now you see when we go to 0, we still only have 3, 2, and 1 because there's only 3 of those guys there. There's no 0 there. Why is there no 0 there? Because I was unable to find an extra state that had the mj equal to m1 equals 2, m2 equals minus 2. That state doesn't exist. Or m1 equals minus 2, m2 equals plus 2. Again, that state doesn't exist. That means that I can't find another state that has mj equals 0. There's only 3 ways to do it, which means I only get the 3 states that I had before, which I must have because I can always hit the state that had mj equals 1 with j minus operators, and they have to give me good states because I'm just lowering mj. Okay? And then, of course, it just continues, and we have this. We can summarize the states that we have, the 3, 2, and 1, and then the 3 and 2, and then the 3 as we lower the mj values. Okay? So this is an important example for you to carefully look at and carefully understand because it is showing you very clearly how this works and why there must be a minimal j when the j1 is not equal to j2. Okay? All right. Let's do some counting to check as well. How many states do I have starting from a j min to a j max? Well, each value of j, there are 2j plus 1 possible m states. So if I start at j equals j min and sum to j equals j max, I'll have the sum of 2j plus 1. That'll be the total number of states in the jm, j1, j2 representations. Now, in the j1, m1, j2, m2, that's a product state between the two different angular momentum states. So that is going to have 2j1 plus 1 times 2j2 plus 1 total number of states in that representation. So let's go ahead and do the summation now. The sum of the 1 term is given by j max minus j min plus 1 because I'm just adding the total number of terms in the summation that I'm summing over. The term with the 2j, I'm going to have a 2 out in front. Now, if I summed from 1 to j max of j. That equals j max plus 1 times j max over 2. And then I have to subtract the sum from j equals 1 to j min minus 1. And the sum of j from j equals 1 to j min minus 1 is equal to j min times j min minus 1 over 2. And the 2's are going to cancel when we do that. And you can see here, I'm going to have a plus j max. That's going to give me j max squared plus 2j max. I'm going to have just a j min squared because that plus j min is canceled with a minus j min. And then I have a plus 1 as well. Now what we're going to do is we're going to put in what the j max is, because we know that j max is j1 plus j2. So we're going to plug that in and add up everything together. And we're also going to substitute in for the j max with a j1 plus j2. And now I'm going to equate that with what it must be from the product state, which was the 2j1 plus 1 times the 2j2 plus 1. We multiply that together, we get 4j1 j2 plus 2j1 plus 2j2 plus 1. I'm going to subtract these two equations from each other. So if the first equation, when I expand that out, I'm going to get a j1 squared plus 2j1 j2 plus j2 squared. I'm going to get a plus j1 plus j2 minus j min times j min minus 1 plus j1 plus j2 minus j min plus 1. And then I'm subtracting off the other term, which was minus 4j1 j2 minus 2j1 minus 2j2. Okay, now we're going to simplify that. So I still have the j1 squared. You can see that I'm going to get a minus 2j1 j2. I still have a j2 squared. The j1 plus j2 plus j1 plus j2, that cancels with the minus 2j1 minus 2j2. The plus 1 cancels with the minus 1. I'm left with minus j min squared. And you can see that object, j1 minus 2j1 j2 plus j2 squared, that's just the quantity j1 minus j2 squared. So we find j min squared is equal to j1 minus j2 squared, which means j min is equal to the absolute value of j1 minus j2, which is what we claimed. And so just by doing this counting over the states, we can verify that the j min is equal to the absolute value of j1 minus j2. All right? Okay, so let's go ahead and do our expansion. So I'm going to do the expansion first in representing the states jm, j1, j2 in terms of the j1, m1, j2, m2 states. We simply introduce a complete set of states, which is a sum of a ket bra object summed over all the possibilities. M1 equals minus j1 to j1, m2 equals minus j2 to j2. And then when we multiply that by the state jm, j1, j2, we have this overlap, which is a number. j1, m1, j2, m2 overlapped with jm, j1, j2. That's the Clebsch-Gordon coefficient. And we can do a similar thing for the j1, m1, j2, m2 representation, summing over a ket bra object of the jm, j1, j2 states. And that's the complex conjugate of the Clebsch-Gordon coefficient. We also call it a Clebsch-Gordon coefficient. Now, the phases are always chosen so that those coefficients are real, and then the only ambiguity is going to end up being plus or minus signs, which are fixed by a convention that we're going to use. Okay? So that's going to bring us to the end of this lecture. We're going to go into more detail about how we actually calculate these Clebsch-Gordon coefficients for some different cases. And of course, in the homework, you're going to get an opportunity to work it out for a non-trivial example. All right, that's all that we have. We'll see you in Lecture 13.